Hello everyone and welcome to Handmade Hero, the show where we code a complete game live on stream. Today I wanted to take a second to show how to do something with our memory system now that we have made it so that the memory arenas allocate memory through the platform layer rather than being passed the memory in through the platform layer. There is an additional thing we can do now which we weren't able to really do before that's kind of a bonus. So I thought I'd show you what it was. It is not a feature that really is particularly relevant to the shipping version of the game, but it is a feature that's relevant to debugging the game. And it's a feature that potentially could have caught errors that we've already had on Handmade Hero. In general, I think it's a worthwhile kind of thing. It's the kind of thing that doesn't catch bugs all that often, but when it does catch bugs, they are bugs that would have taken you probably a little while to find. And so it's kind of a valuable thing, and it doesn't take too much. You can implement it once and have it forever, so it's not like a thing that's particularly difficult either. So let me go ahead and explain what we're going to do here, and it'll take me a couple minutes to kind of get around to it. But basically what we're going to do, today is day 345, so if you want to follow along, use day 344 as source code. What you want to do, when you're programming obviously, is you want to have some ways when you're doing low-level programming like this, where you can catch the kind of bugs that might take you a while to find. And one of the most sort of insidious versions here, right, is buffer overruns, right? We all know that these are particularly problematic. I don't know if I spelled that right. Overruns. It's things where we sort of, we allocate this much memory and then someone's like writing into it and somebody writes over here, right? But there happens to be more stuff here because the actual allocated block, let's say, was that big. So something else is here and this person who was trying to write into here got some pointer math wrong and wrote into here, right? It's one of the kinds of bugs that people even created higher level languages to solve to a certain extent, right? People don't like having buffer overrun bugs. They're tricky to find, tricky to know if you have them, because they typically depend on the actual runtime parameters of the code. They're not usually catchable at compile time always. So, static analysis tools can't always find them for you, blah, blah, blah. And so, it's the kind of thing that is a little bit problematic in C when you're doing this kind of code, but you would like some way of being able to still program in C. You don't want to have to switch to something else just to find them. So the question is, how can you find them maybe more effectively in C? Well, one of the nice things about the way that we're working with our code now is since we're in control of the platform layer, we can do basically our own buffer overrun detection. So if you remember, we use a function called virtual alloc, right? And what virtual alloc does is virtual alloc is essentially, we think of it as an allocator because conceptually that's what it's doing in our program. So when we think about allocating memory, we kind of think about this idea that when we allocate memory, we are kind of getting this memory. We're like acquiring it from the system. And when we free memory, we're releasing it back to the system, right? That's kind of how we look at it because that's what it semantically means to our program. But technically speaking, that's not really that's not the entirety of what it's doing, right? Yes, it is doing the sort of allocation and freeing operations as we would think of them semantically, but we've also, as we've talked about in the past, it also does memory mapping. And what that means is that if we have some kind of physical memory here, right? Here is our physical memory. And this is however much it is. I don't remember how much is on this machine, physical memory-wise, performance. What do we have? Physical memory, 12 gigabytes, I guess, something like this. So, if we have 12 gigs of physical memory, right, then obviously that's all the memory that we're operating with that's actually real. But our programs might be allocating drastically more than 12 gigabytes if we wanted to, right? And even if it wasn't, even if, let's say, we're only allocating a little bit of memory, there's nothing to say that two programs might not be allocating memory in effectively the same place, right? So how does this work? Well, as we've talked about before, in addition to physical memory, there is the concept of virtual memory or virtual addressing space. And what that is what memory looks like to your program. So in a virtual address space, I may think that this block of memory, right, is right here. And maybe I said I allocated 8K of memory, right? And this is where it was in my address space. And so I just think of it as I've got a pointer in here and I do some stuff with it. And as far as I know, it's just whatever the pointer was is where it is in virtual address space, right? But in physical memory, the operating system has mapped this memory that I'm using into some place in physical memory. It may have nothing to do with these addresses. First of all, the operating system works on 4K pages, so theoretically, this might not even be in the same space. It might be that there's some up here and some down here. Like here's 4K of it, the first 4K, and here's the second 4K. Or this could be this could be the first 4K and that could be the second 4K, right? It could be mapped like this. So essentially, there is a page table and all sorts of things that happen that translate these virtual addresses into physical addresses, and the processor has a little table, a translation look-aside buffer, and all these other things. There's just a whole bunch of mechanics that go into making this work smoothly. The end result, of course, being that our CPU, when we are executing our process, as far as we know, it looks like we've just got all this memory that just belongs to us, and that we're talking about it in our terms. But really, the operating system may be moving things around. They may be in various places in physical memory. They may be evicted out to the disk when our process is suspended. All sorts of things can happen, right? So again, we've talked about this on Handmade Hero. I'd encourage you to go back and watch the original episodes on that if you're uncomfortable with it. But that's the basic idea of what happens with virtual and physical memory. So what this means is that we can actually play a bit with how this memory works, because we know that these pages are really part of a scheme that translates addresses into physical memory. It's not like the old days before memory management units, when a pointer actually meant the physical place in RAM where this thing was. That is not what we're dealing with. We're dealing with a virtual address space. So if you think about what happens when we allocate something, right, we call virtual alloc, and we're going to get a pointer to the beginning of whatever this is. And that buffer is going to be 64K aligned. The reason it's going to be 64K aligned is because when you allocate something with virtual alloc, it always gives you back things on 64K page granularity. That's the granularity of NT's allocation, of Windows' allocation. That's it's an operating system specific implementation detail. And then what it's going to do is it's going to allocate some number of 4K pages. The operating system works in these 4K pages. So if we said we wanted 16K, it would not give us a single 16K block. What it actually gives us is a set of blocks that are each 4K that just happen to be contiguous. Okay? So if we ask for 16K, we're actually going to get 4K blocks that all just happen to be mapped contiguously in memory. But when we go through this memory, make no mistake, if our pointer is the pointer, or anything up to the pointer plus 4K minus 1, right, plus 4095, right, we are writing into this memory page. But as soon as we go to 4096, right, now we're pointing into this memory page. And they are actually different to the operating system. Everything inside this 4K page is the same. Everything inside this 4K page treated the same. But between the two, they are not the same. What that means is we have the ability to actually allocate memory in such a way that would create what's called a guard page. And I mean, technically, a guard page is usually used for something slightly different, but it doesn't matter. Point being, we can do something where we allocate an extra page of memory so that, let's say we did want 16K worth of memory, we could then allocate an additional 4K page on the end, so actually 16K plus 4K, so over 20K total, and we could then do something using a new function which we have not used called virtual protect. And what we can do with virtual protect is say, do not allow anyone to write to this page. If anyone writes to this page, I want you to hard fault right there. Okay? So what will happen is people can write. As soon as somebody writes over this page, bam, it's over. Right? It will fault as if we had written to a null pointer. So now you may be saying, well, that's all great. How are we going to deal with the fact that this 16K buffer may actually have been much more unaligned than that, right? What happens if the person only wants to allocate, let's say they allocated, I don't know, 73 bytes. That was the allocation size they asked for. Well, 73 bytes is going to end up being like this little tiny part of the 4K page, right? So now, yes, we could allocate an additional 4K page here and mark it as something that cannot be written to, but there's still all of this buffer overrun space. What that means is that there's still plenty of room for error that we won't catch. And since buffer overruns often tend to be only by a little bit, like it's very common, for example, to maybe have an off by 1 error, it's not so common to have an off by 1,734 or whatever, right? So it's definitely the case that we would like to have the very last little piece here, whatever the one closest to the allocation is, we'd like that to fault. And the answer here is that's actually not that big of a deal if we want to do that. All we have to do is when we allocate memory, if we want to put our memory allocator in a mode that guards for buffer overruns off the beginning of a buffer, then we always just take and we align ourselves such that whatever the pointer is that we return from our allocator, right, is aligned at the beginning, and we mark the page, the 4K page before it, here are the two 4K pages, as unwritable. On the other hand, if what we wanted to do was catch buffer overruns that go off the far end of the buffer, then we just move the pointer up to the end of the page that we get so that it ends right on the page boundary, right? And then we mark it. Now, we can't quite do this always, because if the person who allocated the memory asked for alignment of a certain kind, we may not be able to move it all the way to the end. For example, if they asked for 73 bytes, but they wanted it 16 byte aligned, right? Well, then there's nothing we can do about it, because 64 bytes would be the previous 16 boundary, right? And then 80 bytes would be the next one. And so we're going to have a 7-byte overhang there regardless. There's nothing we can do about that you could overwrite to. But fortunately, usually when people ask for aligned memory, they typically also specify a size that happens to be aligned to that. That's just the way programming typically works. If I'm operating on SIMD, so I'm allocating M128s, typically I'm going to have an even multiple of M128s, which are 16 bytes, right? So it all works out in the end. Previously, we didn't really have any way to implement anything like this, and the reason we didn't is because we were never actually asking the operating system for memory except for just at the very beginning of the program where we asked for one big block. And one big block doesn't really help us, because every time the user does an allocation, they were sub-allocating out of the block. We had no ability to align and protect memory for them in that circumstance. But now that we do have the ability to have our allocator go down through the system, and allocate its memory directly from the OS if we should choose to do so, we can effectively implement bounds checking by forcing it to do that. And let me show you what I mean. Again, just a reminder, we're starting with day 344's code here. Excuse me. I'm going to load up the Handmade project, build it. Here is the memory. And so what I want to do here is say, all right, here's my memory arena. And I have these allocation flags that I'm passing down to the operating system. And what I might want to do is just say, okay, those allocation flags that I have, what if I were to specify another type of flag that says that we want to do that kind of overrun checking, right? So if I do that, should be platform mem, right? Yeah. If I say platform memory, overflow checked, or platform memory like underflow check, then I should be able to specify per arena that I want this. Now that I think about it, this is probably just a thing that we'd turn on at runtime and not for any particular arena. Well, I'll do it per arena for now anyway. Why not? All right. So all I want to do now is say, hey, those allocation flags could be set to underflow check or overflow check. And so if those flags are set, then we know that that's something that we want to have happening on this arena, that debug option. We want to have that on the arena. And so what I'm going to do is in here where we have push size, all I want to do inside the push size is I just want to go ahead and say, hey, let's assume that if this arena has the allocation flag set such that it wants some kind of bounds checking, right? So we just go ahead and say, let's see what the allocation flags say. If their overflow check or underflow check is on, then what I want to do is instead of doing any of this, and I guess technically some of this I do want to do. For example, I do want to do that, right? I do want to be able to do my 0 size. So that should happen regardless of what's happening. But here what I want to do is say, okay, if we're going to underflow or overcheck, instead of doing all of this stuff that we were doing before, I want to instead use essentially a new block for every single one of my allocations, right? So I want to effectively pass every allocation down to the system every time, if that makes sense. So what I can do here is just say like, okay, normally we're calling this only when we need a new block. Instead, I'm just going to call it any time that I have anything happening at all. And so I'm going to declare the result up here, like so. I'm going to get it like this. And then I'm going to keep that path working the way that it was. And so what I'm going to do here is say, like, all right, we've got these allocation flags. We want to do overflow or underflow checking. In that case, let's just allocate the memory, and we'll pass the allocation flags down to the system as is. And that's it. And now everything that we do would actually go through an individual allocation, right? Now this is going to be incredibly inefficient, right? This is definitely not something that we would ever want to do in practice when we were running the game, but it's certainly something we could do for working on the game. So I'm going to go ahead and furthermore pass the size in it down there. There we go. And we also need the alignment here, but this will always be aligned to a 16-byte boundary at the moment, so we shouldn't actually have a problem with that. Okay, so now if I run it, nothing in particular is going to happen, obviously, because we don't actually have that flag set anywhere. So in theory, we just get the exact same thing. But if I am to now go and say, hey, let's by default set those allocation flags. So, you know, let's just say we're going to have a little way in here where we just say, let's OR it in. I'm going to put overflow checking on this arena, on every arena, basically. Then you can kind of see things are super slow, right? And they're because they're allocating, and it can't ever free, right? And so eventually we'll just use up all the memory in the system and just crash, right? In fact, this was probably a bad idea because now our thing is going to crash. That's not good. Stop. Everyone stop. No. Make it stop. Please. Internet worm. The internet worm. I don't understand how we have operating systems still in this day and age. When something just allocates a bunch of memory, it's basically a distributed denial of service attack, right? It's like, how did that happen? And I have no idea. Oh, computer. It's just like in the old days when you didn't actually have memory protection and you'd write a program and it would just crash your computer and that would be the end of it. For the love of God, man, just close the application. How hard is it? You're an operating system. Have some self-respect. Windows! How are you not? Yeah. Ladies and gentlemen, it's 2016, and all you have to do to kill Windows is just allocate some memory. Well, that was fun. Are we still recording even? I have no idea. And we dropped quite a few frames, to say the least. But hey, that's fine. Anyway, I was just trying to show that we could pass all of our allocations down to the system. Oops. Wow. All right, anyway. So the problem that we'll have here if we want to run in this mode for a extended period of time, as you saw, is we do need a way of freeing this memory when the time comes. And so in order to do that, we do need to have sort of a way of keeping our block footer and that sort of stuff, which is these things here. And so what I need to do is I need to have some way that I can still do the like freeze, you know, as we go. So in order to do that, what I want to try and do is I want to try and use the same path. Because you can see, like, I could go here and try to put in the block header and do all that sort of stuff and you know, try, I don't know, monkeying around with it and whatever. But as you can imagine, if I do that stuff, I gotta kind of re-implement all the stuff that I had here before. Because I already had the concept of sticking a footer on the end and knowing that I freed it and that sort of stuff. So the question is, can I do anything here that would force me to always allocate a block and make that be the default thing that happens? And the answer is yes, I can. Because you can see here that previously we were checking to see whether the arena had a particular size or not. And we had this sort of minimum block size and all that sort of stuff. What I could do instead is when I detect that the arena has this particular piece, this particular flag set, what I could do is just change the way that this particular thing works to ensure that arenas never actually keep any size other than the exact size they need for the allocation they just did, if that makes sense. So what I want to do here is say, like, oh, okay. If I am I have to think about whether this getting effective size for here is a problem or not. But if I am detecting that I have the overflow or underflow checking enabled, then what I want to do is I want to say, okay, let's, instead of trying to re-implement exactly the same thing we have there, let's just make sure that we never try to allocate more than exactly the size that's going to give us what we want, right? And in fact, we can still leave this code in there. That won't really make any difference. But what I want to do is, you can see here we do this maximum size plus memory block footer, arena minimum block size. So what we could do is just say, like, hey, always zero out that minimum block size. In fact, maybe I could put it like this. I could say, just make the minimum block size always be 0. Typing is hard. There we go. Get this microphone over. There we go. Let's just always make the arena block size 0 if we're going to do an underflow or overflow check. That way, the amount we allocate is going to be exactly the right amount and never any different, right? That way, we'll always sort of chain the blocks together still, and off we go. So let's give that a shot. And let's see if we're going to hose the system again. Hopefully, we should be freeing things now, although we don't appear to be. Looks like we have stabilized. All right, so that looks fairly stable now. And that, again, is calling strictly through the operating system's allocator for every single allocation. And you can see that we get kind of sluggish performance as a result. Because, again, even the debug system is going through all of those allocations, which is not great, right? But that's it, right? So now we're getting allocations on every call. And so now what we need to do is say, well, okay, depending on whether we want to check for overflows or underflows, we're going to want to put the memory block footer on different sides depending on which one we're checking for, right? If we're checking for overflows, we would want to put the memory block footer at the beginning. If we're checking for underflows, we want to put the memory block footer at the end, right? Because we need the memory block footer to be out of the way so we can line up the thing with the page exactly where it should be. Now I need to double check that the memory block footer is not going to change our alignment. It looks like it would. Looks like our memory block footer currently would, because you can see this is going to be 3 instead of 4 of these. So I'm going to put a pad in here. That's what the memory block footer should probably look like if we're going to move it. And I feel like calling this a footer is probably not right because we might move it around now. So I'm going to call this a memory block chain. There you go. All right. So what I'd like to do now is say, OK, let's allow ourselves, well, first of all, what we can do is let's try to catch overruns off the beginning of a buffer, because that one will work automatically. That one we don't have to do anything really to change, because we've already put our footer we already put our memory block chain information at the end of our thing, at the end of our allocation. So, you know, if you take a look at when we allocate this, oh, I killed Milton. I'm sorry, Milton. I allocated too much memory and now Milton is unhappy. You can close Milton. Go ahead. Go. It's okay, Milton. Milton. What's wrong, Milton? End process. There we go. Let's just go ahead and get our Milton back. There we go. All right. So what we are doing right now is just saying, well, OK, we know that we have a footer on the end right now, right? There's our Mr. Footer. And so since we've got a footer, that means that if we wanted to, the easiest thing to do would be to mem protect the part before our allocation so that we'd catch overwrites that go before the buffer in question, right? So if I want to do that, what would I have to do at the operating system level, right? And so let's take a look at that, because that's the actual interesting part of the implementation here. So when we do platform allocate, Win32 allocate memory, here it is. When we do Win32 allocate memory, then here you can see the virtual alloc call that we're making. And like I said before, what we want to do here is we want to make sure that we have one 4K page at the beginning of our memory block, so that when we go to do overwrite checking, what's at the beginning will be a blank page that we control, right? So if we wanted to do that, it's pretty easy. Let's say I just wanted to do that without checking the flag. Although I could even do it with checking the flag here. I would just say the total size is going to be that. And then I could say, well, if the flags are including underflow checking, then what I want to do is I want to add 4K, right, one page. And I'm probably going to just make that a constant. Maybe I'll even make that to do. So I'm going to add one page worth to the total size so that when I allocate it, I will actually get that extra page that I wanted. So I'll get one page plus however much we actually wanted to have happen. And then you can kind of see here where we do our get base pointer off of block or whatever. What did we do? Did we actually put this at the beginning, I guess? It looks like we did. So yeah, so we've kind of got this, it looks like we've got countervening problems here, right? We put the memory information that we needed on this guy, sort of the loops for the chain for our saving to disk. these are actually placed in kind of an inconvenient location, if that makes sense. It's on the wrong side of it. And it also strikes me again, and you see this pretty often, I prefer it when we don't actually have this problem. So I don't know if we're going to want to try and get rid of it a little bit. There we go. I prefer to not have so many people sticking things onto allocations. So like it's kind of annoying to have both of these things on there. And we can talk about that a little bit separately. But so what I want to do here is I want to say, okay, how do I deal with this particular thing being in the way? And one thing, now that I think about it, maybe that would be an easier way for us to deal with this is I could make it so that I suppose I could make it so that you just get back kind of that chain, because both people basically want to know the same thing, right? The arena is only tracking those blocks because it wants to be able to unwind memory. And the Win32 allocate memory call is exactly doing the same thing, right? It's just trying to keep a linked list of all the memory that's in the system. So really, if we wanted to, we could just make it so that the arena and the memory allocator on the Win32 side actually could just have the same data structure being used for that process, if that makes sense. I kind of feel like we're going to want to do that, possibly before this. Had I thought about that, I would have said let's do that before this. I'm kind of right in the middle of this now, but what are you going to do? All right, so let me just finish the basics of what we're doing, and then we'll go talk about that. So anyway, when we actually do this allocation here, you can see what happens is once I get back this memory block, I'm sort of treating that as the actual block. And what I would rather do at this point is I want to kind of move that block upwards a little bit, right? I want to move that block up to, I want it to start thinking of the memory block as being after the additional size that I sort of said here. So, if I'm in this underflow checking scenario, I want to do that adjustment where block is going to be equal to, one page past wherever virtual alloc gave me back, right? If that makes sense. Okay. So that just allocates an additional page at the beginning of things. That's all it's doing, nothing particularly fancy. So again, the game runs exactly the same, except it's just allocating an extra page of memory every time it was doing an allocation. And so then all we have to do is when we want the underflow checking to occur, we just need to be able to take this block, this original pointer that's that original page, and we just need to virtual protect the page, right? So let's take a look at that call. I talked about it already, but it's the one that we need to use. If we call virtual protect, here is virtual protect. If we call virtual protect, in this case, and we say, all right, here's the address that we want to protect, here's the size, right? We know those two pieces of information. We know we want to protect one page. We know it starts at block. Then all we need to know here is what we want to do to this page. And you can see in, here we go, in this list of constants, what the things that we can do are to the page. So every memory page in Windows, and generally speaking, this is sort of like a function of the processor and the operating system, depending on what sorts of things they both support. But any given memory page, one of those 4K pages in memory, can have any number of bits set that say what's allowed to happen on it. So you can see we've got page execute here. And what that means is that if the instruction pointer for your code were inside this page trying to read code bytes from it, it would be allowed, right? Oops. And that's all that means, right? You can't write to it. You can only execute code out of it. Page execute read means that you could execute code in it or read the data out of it, but still not write to it. Execute read write means you can do everything. You can read from the page, write to the page, or execute code that's in the page. Page execute write copy is a bizarre kind of thing. This is like for Unix fork and stuff like this. It basically says that when you are going to use a particular page, if you were going to execute that page, if you're going to actually run something in that page or write to that page, it would go ahead and duplicate that page to a new page, if that makes sense. This is for stuff, I believe, like fork. You don't typically use it that much outside of that, but you could imagine why you might want it, right? Page no access is what we're looking for more. It just means like if anyone touches this page, it immediately should fault. Page read only is that you could read from the page but just never write to it. Page read write is exactly what it sounds like. Anything except executing code in the page is fine. Page write copy is the copy on write version that does not allow executing out of it. So again, for the Unix fork command kinds of style stuff, you clone all of the address space of a process, and then anytime you write to one of them, it's going to clone to a new page. Page targets invalid and page targets no update I have never seen before. I have no idea what they do. Set all locations of the pages as invalid targets for CFG. Use along with any execute page. CFG is what? What is CFG? I don't know. Pages in the region will not have their CFG information updated while the protection changes for original protect. Simple the pages region. I have no idea. No idea what that is. You're on your own. Page guard. These are basically like the things that are used to grow the stack or do other things with guard pages. Basically, what they do is when you touch them, they fire off an alarm, right? They basically are things when, for example, the way that the stack oftentimes works, the program stack works, is you will take a piece of memory that is the initial part. Let me go ahead and... This is why I said back, I was like, it's not technically a guard page. I said guard page because it's guarding us, but it's not really guard page. So what actually happens with the guard page is like, typically what will happen is maybe you have the program stack here. And then what happens is you want the program stack to grow as the program uses more of the stack. So the program is touching, 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 touching. And then when it touches this, you don't really want it to fault. What you want it to do is call a handler that's going to commit this page, right? And then let you know. What you would then do is go allocate some more memory for the stack and guard another page, right? So it can kind of grow out like this. What you don't want to do is actually stop the process from executing and consider an error. So basically what happens when you hit the page guard is it will raise the violation exception so that you can handle it, but then immediately turns off that status so that things that were touching that page can still continue to touch that page, right? And you can resume executing as normal. Oops. Again, we don't care about that. We don't have to implement that. Page no cache is probably exactly what it sounds like, but honestly, I've never used it. And page write combine, same thing. Page write combine, typically you don't set. That's something that's set for hardware access, and so that would turn on write combining for these pages of memory, which is the thing that makes it so that when you do writes to it, it doesn't flush all the writes in order necessarily. They may be flushed aggregated if writes are expensive, blah, blah, blah. All right. And then these enclave ones are the things we talked about with SGX. That's that weird like Intel thing where you lose control of your own computer. It's basically the thing that allows you to have encrypted memory that you can't touch. So that's what that is. Anyway, so all we really care about here is page no access, right? All I really wanted was page no access. So what I want to do here is I want to virtual protect this thing as page no access so that there's no way for anyone to ever touch the page. It's just going to be a problem if they do. And we need to pass one more parameter, which is what the old protect was. So we just have old protect. And now, in theory, we are protecting the page. Now, I'm going to check the return value. Just so we can ensure that it's actually working, because maybe we passed some parameters wrong and we don't want to mess it up, right? So now we have those guard pages happening there. And we can verify that those are happening properly, because now when we get this block back, what we should be able to do, right, if I didn't call this virtual protect, then in theory what I should have been able to do is say, the part that I'm talking about right now, if I was to set the next pointer to say 0 or something, it should be fine, because we allocated that memory and we're just touching it and setting it to 0. But if instead I was to set virtual protect to say that the page has no access, now if I touch the page, we should crash, right? Or not. I said we should crash. Apparently we don't crash. Apparently because we don't have Underflow check on. Let's try that again. All right, one more time. Let's not protect the page. No problem. And protect the page. And we crash, right? So now we have everything we need to create a bounds checker. Right? We have everything we need to make sure that the instant that anyone touches any piece of memory outside of a valid allocation location, we will fault, right? We'll just fault right there. So I feel like I want to be a little bit more efficient potentially than I'm being right now, but I'm just not going to do that this time around. So I'm just going to do the simpler thing here and say, okay, if we're doing platform underflow checking, then we need what essentially amounts to be 2 extra pages, right, is what I'm going to do. I'm going to say 2 times page size. And I'm going to do that. That is actually what I'm going to do in both cases, right? So I'm going to do, well, I got to add a little bit more to it the other side. So let me just do this one first, and then we'll go from there. So I'm going to add 2 extra pages. I'm going to take excuse me. I'm going to take the block here that I was going to use, and I'm going to put that in the first page. I'm going to then protect the second page, and I'm going to make the third page and up be the stuff that's actually protected, right? So it's just super, super piggy, not good at all, but that's just what I'm going to do temporarily, just to sort of get this working the way that I want it to work first. And then tomorrow I think I want to try and sit down and figure out, can we work out a nice way to make it so that all of these things kind of collapse down into one, and we'll go from there. So anyway, if we were going to do underflow checking, we know we have 2 extra pages. That means that we have the block being where the block actually is, and that's all fine. And so the thing we want to protect is actually the block plus the page size, and we're going to sort that that's protectable. We then have the block itself being where it was originally, but I'm going to introduce the notion that the Win32 there it is, result. So I'm going to introduce the notion here that, again, the get base pointer for a block thing, this is not really going to work anymore. And the reason that this is not really going to work anymore is because if you ask for the base pointer of a block, your problem is that you're going to not know whether this extra padding was happening or not. Now, we could make it a global that you just set for underflow checking or not, and then you would always know throughout all the places. But in this case, you wouldn't really know because we want to allow different arenas to have the overflow or underflow checking on or off separately, right? So what I want to do here is say, okay, inside the memory block, let's just go ahead, since we also have, since we have plenty of extra padding in there, I'm just going to say that we have a base pointer so that basically you can always get from the block to the result without calling get base pointer. It's just is the base pointer, right? And so I'm going to say here that the base pointer, in most cases, is just going to be the block plus 1. But in the case where we actually have some kind of checking turned on, it's going to be something else, right? So in this case, it's going to be 2 times the block size, and off we go. So then we know we always return the base pointer, and we can also get rid of get base pointer for the block, because now it is just a thing that's off of it directly, right? Okay, so moving on. What are you unhappy about? I did say 2 times page size, right? Yes. So, got a little sloppy there at the point arithmetic. Where is my block? Virtual protect. I actually meant to only go the page size up, not the page size times the size of a block, but my bad. So yeah. So now what we have to do is we have to figure out when we're virtual freeing things. Well, we've got a couple things we have to do. But first of all, when we virtual free things, we can no longer assume that the block itself is the actual pointer that we're virtually freeing, right? And the reason for that is because now we may have put the block in some location that has nothing to do with the memory that we're actually returning to you. So we do now need to lean on the thing that I was talking about before, where, like we've got this thing here where we're deallocating memory, we're expecting to get back from the block. We actually need to get down to the base of our allocation again. And in order to get down to the base of our allocation, we need to do the virtual query call that I was talking about before. And the virtual query call, I believe, should give us the piece of information that we actually needed. Where are you? Did I not type that in right? I thought I typed in virtual query. Maybe I didn't. It's right there. And so in this case, what I can do is say, okay, all right, maybe not. So that won't help us either because this has to be the base address of the region of pages. So I can't actually round it down. This is tricky. I guess I'm just going to have to... pass that information to free as well. Because it won't know, it really wouldn't know which one it would have no idea how to get back to what it needs to get back to. You know what I'm saying? So, yeah, it's just kind of tough. But anyway, again, not the end of the world, because we can figure this out by just passing that in, and I'll show you what... I'll show you that it is relatively easy to make sure that as long as we always know what we're doing, we can always back out the pointer to something which will be correct if we know which one we're doing. So let's go ahead and say platform here needs to take symmetric flags so that we can work backwards. Then when we go to Win32 memory, we can do the reverse operation. So here we are with block, and in this case what we want to do is say, oh, well, if what we were actually doing is we were in an underflow checking scenario, then for underflow checking, we would like to say that the block, if we assume that it was, say, a U8, we would like to say that whatever the block is that we gave, that we're getting in here, or rather, whatever the memory is that you're telling us to free, we know that that's 2 pages up from what it should be, right? What I might do here is, because I would like to make this a actual thing, a little Win32 or page size, little variable. Yeah. I know that I just have to subtract 2 times the page size. And I will get back to where I'm supposed to be. Now, I still should be able to do all the rest of my operations because I should be able to always find it when we know we're in an underflow checking scenario. I should be able to go back and find the block in the location that it now is, right? And so in theory, now we're all good, and we're mem protecting those pages. So if anyone tries to underflow even just a little bit, they would immediately fault, right? And so previously, if we wanted to try and catch one of these, for example, let's say we went into Handmade memory and turned this off. So we're not underflow checking anymore. We're just doing the regular kind of running that we normally would. Here's our 16 frames a second. And so let's say I went into some place kind of touchy. Trying to think of what the best place to do this would be. But let's say that I went in somewhere to maybe like world.cpp. And let's see. So we have a thing where we're taking, where we get a first free chunk here, and we're allocating one of these like world chunks. And let's suppose that I was just to touch something right before the first free chunk. So let's say that I have my first free chunk on here, and I'll cast that to a U8 or something like this. And I'm going to go ahead and set a few things back from it to be 0. So I'm just writing off the end of that buffer, right? So that's like plainly illegal, right? And it's definitely a bug and could easily be overwriting something important. We'll never know until we see some really weird behavior and are totally mystified, right? But in theory, if we've done our underflow checking right, now when we do that, it's not only does it catch it immediately with no debugging effort, but it also puts us right on the line that was the bug, right? So again, really, really powerful, because who knows how long a bug like that could sit in the code base without us ever knowing it's there. Then we see a problem later on. We're never going to suspect that part of the code because we haven't touched it in forever, right? So when you're doing that kind of low-level programming, it helps to have tools that allow you to catch problems like that. So if I remove the offending line of code, now we can run through our checker and it works okay, right? So let's try exactly the same thing now. When we do the first free chunk push there, let's try, we only pushed on just this world chunk. Let's go ahead and try going just one after it, right? So I'm going to say writing one after it. And you can see again, now we're overwriting memory, and again, nothing is happening, right? We're not getting any kind of an error there. It's just fine. So we would never know that was happening until we actually see a symptom of the overwrite. So what we want to do now is say, like, okay, we now want to be able to implement our overflow checking. Overflow checking would work exactly the same way. It's trivial for us to implement at the Win32 side of things. Unfortunately, down here, it's a little bit nastier. The reason it's a little bit nastier over here is just because now we've got a situation where we need to move the blockchain that we're actually using here. We need to move that out of the way. And so this is, again, why I say, what I think we want to do in this scenario is we would like to make it so that these two things work in concert a little bit more. I almost just feel like we should be able to get the blockchain stuff back from, like that blockchain is a very simple thing. It's just this, right? And if you take a look at what's going on in the lower level code, it's the same stuff, right? It's exactly the same things. We just have to add the used, right? We just have to add that used value. And so I kind of feel like almost what we want to do is just elevate this construct up. But I don't want to start that now because we're almost out of time. So I think what I'm going to do is I'm going to say, let's go ahead and say consolidate Win32 and platform non-specific memory headers. And then I think we'll be all set. All right, I'm going to go ahead and go to Q&A. Wait, is Insobot now able to understand that I start the Q&A in another chat, and then it starts the Q&A in the Twitch chat? Did that just happen? Insofar as Insobot is seriously the greatest artificial intelligence that mankind has ever known. When can we get it to the point where Insobot can just do the programming on the stream and I can just go home? Like, when will we actually just have Insobot just does Handmade Hero by itself and we don't even need a human in the loop? That is really the future that we need. I'm following on Linux with SDL because I'm not sure it's worth building on X11 or if Wayland is ready yet. Have you thought about building on X11, Wayland, or both? No, basically on Linux, I don't really know Linux very well, so I don't really have strong opinions about that. Like, probably on Linux, I'll just use SDL or something, or, ask more Linux-centric people which one to use, and we'll write that. I don't, like, on Windows, I know a lot of stuff. I'm not the Windows expert or anything, but, like, I know a lot of stuff about how to structure the platform layers and things like that, so I have opinions about it, but I don't have opinions about it on X11 platforms at all, or Wayland. I've never even used Wayland. I know nothing about it. Other than, like, it's one of those things where, like, it's going to replace it eventually or something. But I don't really, that's, like, not really my area of expertise. I don't ship games on Linux. I don't have a lot of expertise there. Before, when you had fixed allocation, you could do a between run save state kind of thing, if I recall correctly. How would you make that happen with the dynamic blocks? That's what we did yesterday. Authority Chair, do you have any insight into if you're developing this game in a similar time flow to major devs? Example, you spent some time today working on Underflow, Overflow before such a thing came into play. Is this just because of the format of the show? Actually, no, that's not true. We have had Overflow and Underflow bugs already. Well, I don't know if we ever had an Underflow one, but we had an Overflow bug already. It just, normally I would do that day one. Like normally I'd have Overflow checking in there just day one. But you know, I try to structure things based on when we kind of naturally get to them in terms of what we're doing and when it makes sense. And now is when it made sense. In fact, we don't know that we don't right now have some overflow bugs in the code, right? For all we know, when we turn on overflow detection tomorrow, it'll crash somewhere and we'll be like, oh, hey, look, we've got an overrun. Like, we don't even know if we don't have an overflow bug right now. Because we could just have like a very subtle overflow bug somewhere. Why do you look so different from Handmade Hero Day 1? Well, it's been like 2 years, almost 2 years. It's deceptive because it says 345, but I don't stream every night. So it's you know, it's only, it makes it seem like it's less days than it has been. Oh, I see what you're asking. Sorry, Dr. Jeets, I didn't understand the question. You're saying, could we do it if across different runs of the program? Wouldn't you need to muck with the base pointers? Yeah, if you wanted to make it work across different runs of the program, that's really not that hard either. We don't really do that ever on Handmade Hero, so I haven't felt the need. But yes, you can totally do that. All you have to do is just when you call virtual alloc, pass in a base pointer and make that base pointer just increment itself as you do your allocations. That's really it. We just save that, you know, we just have to save that out. Actually, now that I think about it, we wouldn't even have to do that. All you have to do is when you're reloading, you just reload one of those things. When you're streaming out the blocks, you just stream out the base pointer. And then when you reload them, you do virtual alloc and pass the base pointer you loaded off the disk. I know this isn't relevant to the code, but does it seem strange streaming in a different location? No, not really, because it's the same computer and the same monitor. I just moved them. Enemy mouse. Seems that Arena started out as a fast stack style allocator and is now moving towards dynamic heap. You've demonstrated the benefits of virtual alloc, etc., but can you comment on the performance fit and why you chose it over malloc? No, so just to be clear, I'm not necessarily saying that we'll ever run in any of these modes. Probably we'll set the initial allocation sizes of our 5 or 6 arenas to just be one allocation and at the beginning, and that'll be it. So we probably won't really do. We will probably leave it as running in its stack mode, because remember, we haven't changed that at all. The only thing we added was the fact that when you overflow, we will allocate a new page. So basically, right now, we're just running in modes, like I'm playing around with, like, for example, here's the debug mode we can use or whatever. But you never want to take this branch. Like, this branch just doesn't ever want to be taken. And most of the time, it's not, right? So it still ends up being a very fast stack-style allocator, provided that you seed it with a good default page size for the arena. William Bundy, it is James Horner's main theme from The Rocketeer. Windell, are any days missing from the YouTube archive? Not that I know of. As far as I know, all days are on the YouTube archive. Was memprotect the primary motivation for moving to dynamic memory, or were there other reasons? Like I said, I don't really have any motivation for moving to dynamic memory. I just wanted to show how you could do it. The game will run in either mode, right? You can, if you would like to, just get rid of this path and then go back to having arenas allocate a big chunk at the beginning, and that would be fine. So I don't want to suggest that one is like good or bad. It's just whichever one you want. And I wanted to show how that can be done. Like, the game doesn't really have to change at all, right? As long as the game just uses a push style setup for its own purposes, then you can pretty much just choose whether you're doing dynamic allocation or non-dynamic, right down to individual structures, if you want to do protected pages. But again, that's really only for debugging. You don't ever want to do that. You don't want to allocate and protect extra pages if you're not in a debug scenario, because it just allocates way more memory. And it's much slower too, because it has to actually do a memory allocation every time we do a push struct, whereas normally every time you do a push struct, it's just incrementing the pointer over. All right, looks like no more Q colons, so I'm going to wrap it up. All right, thank you everyone for joining me for another episode of Handmade Hero. It's been a pleasure coding with you as always. If you would like to follow along with the series at home, you can always pre-order the game on handmadehero.org or Go to the forums to ask questions. The Patreon page supports the video series. The schedule bot, which tweets a schedule at you, or our past episode guide, where the old episodes are. I'll be back here tomorrow for the last stream of the week. Not streaming on Friday. I'll be back here for 5 p.m. Pacific Daylight Time. Hope to see you there for that. Until then, have fun programming, and I'll see you guys on the internet. Take it easy, everyone.